Imagine standing on a plain of gray dust, the ground cracked into long ridges that stretch toward a black horizon. Above you, the sky is not blue. It has no color at all because there is no air to scatter light, only the deep and total black of open space, even though the sun is close enough to feel like a physical weight pressing on your shoulders. You watch it rise. Slowly, almost lazily, it climbs into that black sky, larger than you have ever seen it, more than twice the size it appears from Earth. And then, as it nears its highest point, something strange happens. The sun slows. It stops. And then, for a few days, it drifts backward, retreating the way it came, before pausing again and continuing on its original path. No cloud caused this, no trick of the eye. It is the honest motion of the sun in the sky of Mercury, a planet so close to its star and so strangely tuned in its spin that the very sky obeys rules that feel almost like a broken clock. This is not the version of Mercury you were taught in school, the tiny gray dot at the edge of every diagram, mentioned for perhaps 10 seconds before the lesson moved on to something more colorful. It is a place of doubled sunrises, of a day longer than its year, of ice hiding in eternal shadow on a world otherwise scorched past the melting point of lead. And Mercury is only the beginning. Venus, Earth, and Mars, the four rocky worlds we call the Tellurian planets, were each handed a single paragraph in most textbooks, and then quietly set aside in favor of the gas giants, the moons of Jupiter, the rings of Saturn. But these four small solid worlds, formed from the same swirl of dust nearly 4.5 billion years ago, took four wildly different paths. One became an iron heart wrapped in almost nothing. One turned itself into a greenhouse so extreme it could melt tin on its surface. One became, against long odds, a garden, and one dried into a rusted memory of a wetter, thicker past. Tonight, we are going to walk slowly through each of them, not for the postcard facts, but for the strange, quiet details that rarely make it into any classroom. Settle in. There is no rush here. We have four whole worlds to drift through, and the story of each one begins closer to the sun than you might expect. The iron planets start, where the story of the rocky worlds begins, at the very edge of survivable distance from a star, on the planet Mercury. To look at it in a photograph, you would be forgiven for mistaking it for our own moon. Gray, cratered, airless, it seems at first glance like a leftover, a world that never quite became anything. But that assumption dissolves the moment you look at what Mercury is actually made of. Roughly 70% of its mass is metal, mostly iron, with the remaining 30% made up of silicate rock. Compare that to the Moon, which is almost entirely rock, with only a small metallic core, and you begin to see that Mercury is less like a rocky planet with some iron inside it, and more like a ball of iron wearing a thin coat of stone. This unusual composition gives Mercury a density of about 5.5 grams per cubic centimeter, making it the second densest planet in the solar system, just barely behind Earth. If you could somehow inflate Mercury to the size of our planet, while keeping the same materials in the same proportions, it would actually be denser than Earth itself, because so much of its bulk would be iron rather than lighter rock. But Mercury never got the chance to grow that large, and so its gravity remains modest, only about 3.5 meters per second squared at the surface, close to what you would feel standing on Mars, a planet nearly twice its diameter. That single fact tells you almost everything about how strange Mercury's insides must be. Something in its history, stripped away much of its rocky mantle, leaving the iron core relatively exposed beneath a thin shell. The leading explanation, still debated among planetary scientists, is that a colossal impact early in the solar system's life blasted away much of Mercury's outer layers, the way a hammer might crack the shell off a boiled egg while leaving the yolk mostly intact. Another theory suggests that the young sun's intense heat and radiation may have vaporized and blown away lighter material before it ever had the chance to accumulate. Either way, what remains is a planet that is essentially a dense metallic heart with barely enough stone left to call it a proper crust. And that iron core does something else remarkable. Despite Mercury's small size and its painfully slow rotation, the planet still generates its own magnetic field, though a weak one, only about 1% the strength of Earth's. This was genuinely surprising to scientists because generating a magnetic field usually requires a large, actively churning liquid core, something you would not expect on a small, slowly spinning world that should have cooled and solidified long ago. Instead, Mercury's eccentric orbit seems to be the reason its core stays warm. As the planet swings from 46 million kilometers to 70 million kilometers from the Sun and back again over each orbit, the changing strength of solar gravity flexes and squeezes the planet slightly, generating friction deep inside it, the same way bending a metal wire back and forth repeatedly will warm it in your hands. That gentle, continuous kneading keeps part of Mercury's core liquid enough to generate a magnetic field, faint but real, wrapping an otherwise nearly airless world in an invisible, protective bubble. It is a small mercy for a planet that receives, at its closest approach, over 6 times the solar radiation Earth does, and it is the first hint that Mercury, so often dismissed as boring, is instead one of the most quietly strange objects in our entire solar neighborhood. A day longer than a year. Here is a fact that tends to stop people mid-sentence the first time they hear it. On Mercury, a single day, from one sunrise to the next, lasts longer than the planet's entire year. Mercury circles the Sun in only 88 Earth days, a swift, tight loop that makes it the fastest planet in our solar system by orbital period. And yet, because of the peculiar relationship between its rotation and its orbit, a full solar day there, the kind of day we experience, stretches across roughly 176 Earth days, which means Mercury completes 2 full trips around the Sun before a single one of its days has finished. To understand why, you have to look at how Mercury spins. It rotates once on its axis every 59 Earth days, which by itself would not be so strange. But Mercury does not simply rotate once for every orbit, the way our moon does around Earth. Instead, it spins exactly 3 times for every 2 orbits it makes around the Sun, a relationship astronomers call a 3-2 spin-orbit resonance. For a very long time, this coincidence fooled the scientific world. Early astronomers, watching Mercury only during the brief windows when it was visible from Earth, kept observing the same face of the planet each time and concluded that Mercury must be tidally locked to the Sun, always showing one side, just as our moon always shows one face to us. It was not until the 1960s, when astronomers bounced radar signals off Mercury's surface and measured the returning echoes, that the truth came out. Mercury was not frozen in place at all. It was quietly rotating, completing exactly 2 spins in the time it took to complete 3 of those observational windows, a numerical coincidence so precise that it had fooled observers for centuries. The consequence of this 3-2 resonance is the Sun's bizarre choreography across the Mercurian sky. Because the planet's rotation and orbital speed only align neatly twice per orbit, and because Mercury's orbit is so eccentric, meaning its distance from the Sun varies dramatically throughout the year, the apparent motion of the Sun, as seen from the surface, becomes genuinely unpredictable to the eye, even though every part of it can be calculated with total precision. Near perihelion, when Mercury is at its closest approach to the Sun, the planet is moving through space faster than it is spinning, and for a handful of days, this causes the Sun to appear to slow to a stop and drift backward across the sky before resuming its normal path. Stand at the right longitude at the right time, and you could watch 2 sunrises in a single Mercurian day, the Sun peaking up, pausing, sinking slightly back below the horizon, and then rising again properly hours later. It is worth sitting with that image for a moment, a place where the sky itself seems to hesitate, where the most basic rhythm we know, day following night following day, becomes something closer to a slow, uncertain breath. And all of this happens while temperatures on the surface swing from over 400 degrees Celsius in direct sunlight to nearly negative 180 degrees Celsius in shadow, because Mercury has essentially no atmosphere to hold or spread that heat around. Only the thinnest trace of gas surrounds the planet, called an exosphere, where the few atoms present are so sparse that they almost never collide with one another. It is not really an atmosphere in any meaningful sense. It is closer to a held breath, a planet standing at the edge of true vacuum, entirely at the mercy of the Sun above it. Ice in the furnace. Perhaps the strangest secret Mercury has been keeping is this. On a planet where daytime temperatures can melt lead, there is ice. Not metaphorical ice, not some trace chemical curiosity, but actual frozen water sitting quietly at the bottom of craters near Mercury's poles. The explanation lies in Mercury's almost non-existent axial tilt, measured at just a fraction of a degree, so small it is nearly impossible to notice at all. Because Mercury barely tilts on its axis, the Sun never rises high enough at the poles to reach directly into the deepest craters there. Inside those craters, permanent shadow reigns, pockets of darkness that have likely not felt direct sunlight in billions of years, and in a place with no atmosphere to transport heat from the blazing daylight side to the frozen night side, those permanently shadowed craters can sit at temperatures cold enough to trap water ice indefinitely, insulated by darkness on a planet otherwise defined by fire. When the Messenger spacecraft arrived in orbit around Mercury in the year 2011, one of its central goals was to investigate radar-bright regions near the poles that earlier observations from Earth using the Arecibo radio telescope had already flagged as unusual. Messenger's instruments confirmed it. These bright patches lined up precisely with permanently shadowed crater floors, and the data strongly indicated water ice, likely delivered over billions of years by the impacts of comets and ice-rich asteroids, the same violent process of bombardment that carved out the planet's countless craters in the first place. Estimates suggest the total ice hidden away in these polar hiding spots could weigh somewhere in the range of 100 trillion kilograms, an amount that sounds enormous until you place it next to Earth's oceans, at which point it becomes almost nothing, a single dusting of snow compared to entire seas. But on a planet this dry, this ice is not trivial. It hints at something we tend to forget when picturing the solar system's inner planets as some tidy progression from hot and dry to cold and icy. Volatile materials, ice among them, are scattered throughout the solar system in far stranger places than we would intuitively expect, tucked into shadows, hiding at the bottom of gravity wells, wherever darkness and cold conspire to protect them from a sun that would otherwise erase them instantly. There is something quietly moving about this, a planet defined by heat, orbiting so close to its star that even its rocks blister, and yet carrying inside its oldest, darkest craters small frozen reserves of the same substance that fills our oceans and falls as snow in our winters. Mercury does not advertise this ice. You cannot see it in any photograph taken from orbit because it lies below the rims of craters, forever out of the reach of direct sunlight and forever out of view from above. It takes specialized instruments sensitive to the faint signatures of hydrogen to even confirm it is there. It is a reminder that even the most extreme environments in our solar system rarely tell the whole truth about themselves at a glance, and that some of the most interesting details are the ones hiding in shadow, waiting for someone patient enough or curious enough to go looking. Sister, not twin. Now travel outward past Mercury's furnace, past the vast gap of empty space between the first and second planets, until you arrive at Venus, a world that for centuries seemed to promise something like a companion to Earth. On paper, the resemblance is striking. Venus is almost exactly Earth's size, its diameter measuring roughly 12,100 kilometers against Earth's 12,740, a difference of only a few percent. Its density and overall composition are similar too. Rocky, iron-cored, formed from much the same raw material as our own world in the same region of the early solar system. For much of the 20th century, before spacecraft actually reached it, popular imagination filled in the blanks with jungles, oceans, even the possibility of dinosaurs, hidden beneath the thick white clouds that make Venus the brightest planet in our night sky, outshone only by the moon. It seemed entirely reasonable to call Venus Earth's twin, a rocky world just slightly closer to the sun, perhaps a touch warmer, perhaps a little more humid. Nothing could have prepared early scientists for what those clouds were actually hiding, because underneath that soft, bright shroud sits perhaps the most hostile surface of any planet in our solar system, a place where the ground itself experiences a surface pressure 92 times that of Earth, roughly equivalent to the crushing weight you would feel a full kilometer beneath our oceans. It is a pressure that would flatten an unprotected human being almost instantly, and it comes not from an ocean of water, but from an atmosphere made overwhelmingly of carbon dioxide, thickened further by clouds of sulfuric acid droplets drifting high above the surface. That carbon dioxide atmosphere traps heat with such ferocious efficiency that Venus's surface temperature averages around 462 degrees Celsius, hot enough to melt lead, hot enough that it is, on average, even hotter than Mercury, despite orbiting more than twice as far from the Sun. Mercury simply has no atmosphere to hold onto its heat, while Venus has built itself the most effective greenhouse trap among all the rocky worlds, wrapping itself so tightly in its own insulation that day and night barely differ in temperature at all. So where did the two planets diverge so dramatically? Formed from similar material, at similar distances from a young sun, why would one become a garden and the other a pressure-cooked furnace? The honest answer is that scientists are still working this out, piecing together clues from orbiters and the handful of landers that have ever survived long enough on the Venusian surface to send back data. One leading idea suggests that early in its history, Venus may have had its own liquid water, perhaps even shallow oceans, but that its slightly closer position to the Sun set off a runaway greenhouse effect, evaporating that water into the atmosphere, where solar radiation gradually broke the water molecules apart and the light hydrogen atoms escaped into space forever, leaving the heavier oxygen behind to combine with surface rock. Without liquid water to lock carbon dioxide into rock, the way Earth's oceans and plate tectonics do, gas that should have been absorbed into the crust instead accumulated in the sky, thickening the atmosphere over billions of years until it became the crushing, blistering shroud we observe today. It is a sobering story because it suggests that the line between a world like Earth and a world like Venus may not be some vast dramatic gulf, but instead a matter of degree, a slightly smaller distance from the Sun, a slightly different starting condition, tipping one rocky planet toward life, and the other toward an inferno that has now lasted for an unknown span of geological ages. The furnace, beneath the clouds. To really understand Venus, you have to travel down through its atmosphere layer by layer, the way the Soviet Venera probes did decades ago, descending through hell to give humanity its only direct photographs ever taken from another planet's surface in visible light. Begin high up at around 250 kilometers above the ground, at the very edge of measurable atmosphere, where the air is thin enough that a spacecraft passing through barely notices resistance. Descend further, and by around 60 kilometers up, you reach the main event, the thick, pale yellow cloud deck that gives Venus its featureless, almost gentle appearance from space. These clouds are not made of water droplets as ours are. They are composed of sulfuric acid, formed when ultraviolet sunlight breaks apart carbon dioxide molecules high in the atmosphere, freeing oxygen atoms that then combine with sulfur dioxide and trace water vapor to create a fine, corrosive mist. These clouds reflect around 3/4 of the sunlight that strikes them back into space, which is precisely why Venus glows so brilliantly in our night sky, even though almost none of that light ever reaches its actual surface. Pushed down further still, through winds that howl at the cloud tops at roughly 300 kilometers per hour, fast enough that the entire cloud layer circles the planet in only about 4 to 5 Earth days, even though the solid planet beneath rotates so slowly that a single Venusian day lasts longer than its year. This mismatch, the atmosphere sprinting around the planet while the ground beneath it barely turns at all, remains one of the more curious unsolved puzzles of Venus, known as superrotation. And while scientists have proposed several explanations involving heat transfer and atmospheric waves, no single theory has been universally accepted as the full answer. Continue your descent below the clouds, and the ferocious winds finally calm, dropping to only a few kilometers per hour near the surface. But do not mistake that calm for gentleness. At the ground, the atmosphere has become so dense that carbon dioxide no longer behaves like an ordinary gas at all, but instead exists in a strange intermediate state called a supercritical fluid, thick and heavy, somewhere between a gas and a liquid, so dense that even a light breeze here would feel like wading slowly through water rather than walking through air. And all around you, at 462 degrees, everything glows with an oppressive, ever-present heat, a temperature that remains almost perfectly constant whether it is day or night, whether you stand at the equator or near the poles, because the atmosphere is now so thick and so efficient at trapping and redistributing heat that Venus barely experiences seasons or day-night temperature swings at all. It is worth pausing here to notice something almost poetic in the wreckage of this planet. Beneath all that crushing, blistering hostility lies a surface with evidence of vast ancient lava flows covering perhaps 80% of the ground, and more than 160 volcanic structures over 100 kilometers across, more large volcanoes than anywhere else in the solar system, including Earth. Radar mapping, since clouds make ordinary photography from orbit impossible, has revealed a surface that appears to have been almost entirely repaved by volcanic activity, sometime between 300 and 600 million years ago, comparatively recent in geological terms, suggesting the entire crust of Venus may have undergone some kind of global resurfacing event, an idea still debated but broadly supported by the near absence of very old, heavily eroded terrain. Somewhere in that ancient volcanic violence, perhaps, lies the true story of how Venus lost whatever gentler past it may once have had. A world turned upside down. There is one more strangeness about Venus worth sitting with quietly before we move on, and it concerns not its heat or its crushing weight, but the simple, almost childlike question of which way it spins. Every planet in our solar system orbits the Sun counterclockwise when viewed from above the Sun's north pole, and nearly every planet also rotates on its own axis in that same counterclockwise direction. Venus does not. It spins backward in what astronomers call retrograde rotation, turning clockwise while it orbits the Sun counterclockwise, the only planet besides Uranus to defy the pattern in this particular way. And it does so with almost unbelievable slowness. One full rotation on its axis takes 243 Earth days. Longer than the 124 Earth days it takes Venus to complete a full orbit around the Sun. In other words, a Venusian year passes more quickly than a single Venusian day. Because of that backward spin combined with its orbital motion, a solar day on Venus, meaning the time from one sunrise to the next, works out to about 117 Earth days, meaning you would experience fewer than 2 full days across an entire Venusian year. And because the rotation runs backward, if you could somehow stand on the surface and watch through the clouds, the sun would rise in the west and set in the east, the precise opposite of what every other planet in the solar system, Earth included, would show you. No one knows for certain why Venus ended up spinning this way. The leading hypotheses involve either a colossal collision early in the planet's history, similar in spirit to the impact thought to have formed our own moon, knocking Venus's rotation into reverse, or alternatively, a gradual process involving tidal interactions between the planet's solid body and its thick atmosphere over enormous spans of time, slowly torquing the rotation until it flipped. Both explanations remain plausible, and without more direct geological evidence from the Venusian surface itself, which remains difficult and expensive to study up close, the true cause may stay uncertain for a long while yet. What makes this rotation especially remarkable is how it ties into another mystery, the near total absence of a magnetic field around Venus. Given how similar Venus and Earth are in size, density, and presumably internal composition, scientists expected Venus to generate a magnetic field through the same kind of churning liquid metal core that powers Earth's own protective magnetosphere. Instead, Venus appears to have little to no significant internal magnetic field of its own. One proposed explanation connects this absence to Venus's extraordinarily slow rotation, since a magnetic dynamo typically depends on relatively rapid spinning to help drive convection currents in a molten core. Another idea suggests that Venus, unlike Earth, never experienced the kind of enormous moon-forming impact that may have helped jumpstart Earth's internal dynamo billions of years ago. Without a magnetic field to shield it, Venus's upper atmosphere is left directly exposed to the solar wind, which slowly strips away lighter atmospheric particles into space, trailing behind the planet in a faint, comet-like tail, invisible to the naked eye but detectable by passing spacecraft. It is a strange, layered irony. Venus, so similar to Earth in raw size and material, ended up different in nearly every way that matters, spinning the wrong direction, moving too slowly to generate its own magnetic shield, and smothered beneath an atmosphere so thick and reflective that from space it looks like the gentlest planet in the solar system, a soft, pale marble hiding underneath its clouds, one of the most punishing environments we have ever measured anywhere. The blue marble's hidden machinery, after the furnace of Venus, arriving at Earth, feels almost like waking from a nightmare into an ordinary, quiet morning. And yet Earth, precisely because it is our home, is the planet we understand least intuitively, the one whose oddities we rarely stop to notice, simply because we have never known anything else. Consider, for a moment, the shape of the planet beneath your feet. Earth is not a perfect sphere. It bulges very slightly at the equator due to the centrifugal effect of its own rotation, making it about 45 kilometers wider across the equator than from pole to pole, a difference so small relative to Earth's total diameter of roughly 12,700 kilometers that from space the planet still looks essentially round. But it is enough that the single point on Earth's surface farthest from the planet's center is not the peak of Mount Everest at all, but the summit of Chimborazo, a volcano in Ecuador that sits closer to that equatorial bulge, even though Everest remains taller when measured from sea level. Beneath that gently imperfect surface lies the feature that quietly makes nearly everything else about Earth possible, its plate tectonics. Earth is the only rocky planet in our solar system known to have an actively shifting crust broken into large plates that drift, collide, and slide past one another atop a slowly flowing mantle beneath. This constant, almost imperceptibly slow churning, plates moving at roughly the speed your fingernails grow, is responsible for building mountain ranges, opening ocean basins, triggering earthquakes, and fueling volcanic activity around the globe. But its most important function may be one that goes almost entirely unnoticed. Plate tectonics acts as a long, slow thermostat for the planet, continuously recycling carbon dioxide between the atmosphere and the crust over millions of years, pulling excess greenhouse gas out of the sky and locking it into rock, then gradually releasing it back out through volcanic activity, keeping Earth's climate within a survivable range across vast stretches of geological time. Venus, lacking this recycling system entirely, has no such thermostat, which may be a significant part of why its atmosphere spiraled into runaway heat, while ours has remained comparatively stable for billions of years. Beneath even the mantle, at the very heart of the planet, lies Earth's core, composed mostly of iron and nickel, split into a solid inner core roughly the size of the Moon, and a liquid outer core surrounding it, the outer core alone stretching across some 5,000 kilometers in diameter. As that liquid metal churns and swirls, driven by heat escaping from the solid inner core and by the planet's own rotation, it generates electric currents that in turn produce Earth's magnetic field, invisible but immense, extending far out into space and deflecting the relentless stream of charged particles that flow outward from the sun. Without this magnetic shield, that solar wind would slowly strip away our atmosphere over time, much as it appears to have done to Mars, and would bathe the surface in a far higher dose of damaging radiation. Instead, most of those particles are guided harmlessly around the planet or funneled toward the poles, where they collide with atoms in our upper atmosphere and produce the shimmering green and red curtains of the aurora, a genuinely beautiful side effect of a planetary defense system running quietly, permanently, in the background of every single day you have ever lived. The Moon's quiet grip. There is one companion of Earth so familiar that it is easy to forget how strange its very existence actually is. Compared to the size of its host planet, Earth's moon is enormous, the largest moon relative to its parent planet anywhere in the solar system, a fact so unusual that some scientists prefer to think of the Earth-Moon system as something closer to a double planet than a planet with an ordinary satellite. Most theories agree that the Moon formed early in Earth's history, likely from debris ejected when a Mars-sized body collided with the young Earth, material that was flung into orbit and gradually coalesced into the single satellite we see today, hanging close enough in our sky that we can trace its craters and mountain ranges with nothing more than a modest backyard telescope. That closeness comes with consequences that ripple through nearly every corner of life on Earth, most obviously in our tides. As the Moon's gravity pulls on Earth's oceans, it raises a bulge of water on the side of the planet facing it, and, through slightly more subtle physics, a second bulge on the far side as well, and as Earth rotates beneath these bulges, coastlines around the world experience the rhythmic rise and fall of the tides, a rhythm so deeply woven into the biology of marine life that entire ecosystems, from the spawning cycles of coral to the feeding patterns of shorebirds, are timed around it. What is less obvious and rarely taught at all is that this same gravitational tug is gradually slowing Earth's rotation, lengthening our days by roughly 2 milliseconds every century, an amount so small it is completely imperceptible within a single human lifetime, but one that adds up over deep time into something remarkable. Roughly 500 million years ago, evidence preserved in ancient fossilized coral and sediment layers suggests Earth's day lasted under 22 hours, meaning a full year back then contained something closer to 400 days, rather than our present 365. The moon, in other words, has been quietly stealing hours from our days for as long as it has orbited us. A theft so gradual it barely registers even across the whole of recorded human history, and yet one that has shaped the length of every single day any living creature on this planet has ever experienced. There is a further hypothesis still actively debated among planetary scientists that the moon's steady gravitational influence may have done more than just move water around. Some researchers propose that the tidal stresses exerted by such a large, close moon could help stabilize the tilt of Earth's rotational axis over long timescales, preventing the kind of chaotic wobbling that computer models suggest smaller, moonless rocky planets might experience. Mars, by contrast, has only two small irregular moons, Phobos and Deimos, far too tiny to exert any comparable stabilizing pull, and some models suggest Mars's axial tilt may have varied dramatically over millions of years as a result, swinging between extremes that would produce far more severe and unpredictable climate shifts than Earth has ever known. If this idea holds up under further research, it would mean that something as commonplace and overlooked as our moon, the pale disk we glance at without much thought on a clear night, may be one of the quiet, essential reasons Earth has remained hospitable to complex life for as long as it has, a companion so constant that its influence has become almost invisible, woven into the length of our days and the stability of our seasons long before anyone was here to notice it happening at all. Rust and wind from Earth travel outward once more past the orbit we call home, to the small, reddish world that has captured more human imagination than any other planet, Mars. It is, in many ways, the rocky planet most similar to Earth in rhythm, if not in scale. A Martian solar day lasts 24 hours, 39 minutes, and 35 seconds, close enough to our own that early astronomers plotting its rotation must have felt an odd sense of familiarity. Its axial tilt, at about 25 degrees, is remarkably close to Earth's own 23.5 degrees, meaning Mars experiences seasons in a genuinely Earth-like way, complete with polar caps that visibly grow and shrink between summer and winter. But those polar caps hide a detail rarely mentioned in passing. While a portion of them consists of water ice, much like our own polar regions, a significant layer is made instead of frozen carbon dioxide, dry ice, which forms during the deep cold of each pole's winter when the atmosphere itself becomes so frigid that carbon dioxide gas condenses directly out of the sky and settles onto the surface as slabs of solid ice, only to sublimate back into gas again once spring sunlight returns. This seasonal freezing and thawing of the very air above the poles drives some remarkable surface phenomena, including strange, spidery dark patterns that appear across the polar terrain each spring, a phenomenon nicknamed Martian spiders, caused not by anything biological, but by trapped carbon dioxide gas building up pressure beneath a translucent layer of ice until it eventually bursts through in localized jets, carrying dark dust up from beneath the surface and scattering it outward in branching radial patterns across the ice. Move away from the poles, and Mars reveals a landscape shaped by both ancient catastrophe and ongoing restless weather. Because Mars's gravity is only about 38% of Earth's, meaning a person who weighs 100 kilograms on Earth would weigh only about 38 kilograms here. The planet was able to build geological structures that would be physically impossible under Earth's stronger pull. Olympus Mons, the tallest volcano in the entire solar system, rises some 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest measured from sea level, and spans more than 600 kilometers across at its base, an area comparable to the entire state of Arizona. Its slopes are so gentle, averaging only about 5 degrees, that if you somehow stood at its summit, the sheer curvature of the planet beneath your feet would prevent you from seeing the mountain's base at all. Nearby, a canyon system called Valles Marineris stretches across the Martian surface for a distance equivalent to the width of the continental United States, 4,000 kilometers long, and in places reaching depths of up to 7 kilometers, roughly 4 times deeper than Earth's Grand Canyon. And yet, despite these frozen, ancient monuments, Mars is far from a dead world. Its thin atmosphere, composed almost entirely of carbon dioxide and only about 1% as dense as Earth's, still generates powerful winds capable of lifting fine dust into storms that occasionally grow large enough to envelop the entire planet for weeks at a time, visible even to telescopes back on Earth, swallowing familiar landmarks beneath a haze of ochre dust before gradually clearing to reveal the same rust-colored ground beneath, patiently waiting out each storm the way it has for countless ages before we ever learned to watch. Ghosts of water. The most haunting feature of Mars is not any mountain or canyon, but the quiet, unmistakable evidence carved into its surface by something that is no longer there, liquid water. Orbiting spacecraft have photographed countless branching channels across the Martian surface, patterns that mirror, almost exactly, the dried riverbeds and drainage networks you would find on Earth after a flash flood has come and gone. Valleys carved not by wind or lava, but by water that once ran across this now bone-dry world in significant quantity, perhaps even pooling into ancient lakes and, some evidence suggests, a shallow ocean covering part of the northern lowlands billions of years ago. For that water to have existed as a liquid rather than instantly freezing or boiling away, Mars would have needed a much thicker atmosphere than the whisper-thin one it has today, dense enough to trap heat and maintain surface pressures high enough to keep water stable rather than evaporating directly into vapor or freezing solid. So the question that has driven decades of Mars exploration becomes almost painfully simple to ask and extraordinarily difficult to answer. Where did that atmosphere go? The leading explanation traces back once again to a planet's magnetic field, or in Mars's case, the lack of one. Evidence embedded in ancient patches of magnetized Martian crust suggests the planet did possess a global magnetic field early in its history, generated by the same kind of internal dynamo that still protects Earth today. But sometime around 4 billion years ago, for reasons still not entirely understood, possibly linked to Mars's smaller size causing its molten core to cool and solidify more quickly than Earth's, that internal dynamo shut down, and the planet's protective magnetic shield faded away. Without it, the solar wind, that same constant stream of charged particles from the sun, was left free to strike the upper Martian atmosphere directly, gradually stripping away lighter gas molecules into space over the following billions of years, a slow bleeding away of atmosphere that NASA's MAVEN orbiter has directly measured, continuing to this very day, watching in real time as Mars continues losing what little air it has left, atom by atom, carried off on the solar wind. As that atmosphere thinned across deep time, surface pressure and temperature dropped below the point where liquid water could survive, and whatever oceans, lakes, and rivers once existed either froze into the ice we still find at the poles and locked beneath the surface, or were slowly lost to space along with the atmosphere that had once protected them. What remains today are only the ghostly outlines, dry channels, and sediment patterns, quietly recording a warmer, wetter chapter of Martian history that ended long before anything resembling complex life had even emerged on Earth. Rovers such as Curiosity and Perseverance have been specifically sent to examine these ancient riverbeds and lakebeds up close, drilling into rock layers that may have formed at the bottom of a lake billions of years ago, searching for any chemical trace, any hint of the organic molecules that would suggest life had once had the chance to take hold during that brief, wetter window before Mars dried into the rust-colored desert it has remained ever since. A planet that seems to be quietly asking us, with every dry channel and every dust storm, what might have been, had things gone only slightly differently. 2 moons, one question. Before we leave Mars, it is worth turning your attention to its 2 small companions, Phobos and Deimos, moons so modest in size that they are easy to overlook entirely, yet each carrying its own quiet strangeness. Unlike Earth's large round moon, both Phobos and Deimos are small, irregularly shaped bodies, more closely resembling potatoes than spheres, likely either captured asteroids from the nearby asteroid belt or debris left over from an ancient impact on Mars itself, a question that remains genuinely unresolved and is one of the key reasons space agencies are so eager to send a sample return mission to Phobos in the coming years. Phobos, the larger and closer of the two, orbits at a distance of only about 6,000 kilometers above the Martian surface, remarkably close when you consider that our own moon orbits Earth at nearly 400,000 kilometers away, over 60 times farther. Because it sits so close to Mars, Phobos completes an entire orbit in under 8 hours, meaning it would rise and set multiple times within a single Martian day, moving fast enough across the sky that an observer standing on the surface could watch it visibly crawl from horizon to horizon in a matter of hours, rather than the slow overnight arc we are used to from our own moon. But that closeness carries a quiet, almost melancholy consequence. Phobos is gradually spiraling inward toward Mars, drawn by gravitational tidal forces in much the same way our own moon is slowly drifting away from Earth, only in the opposite direction. Current estimates suggest that within the next 30 to 50 million years, Phobos will either crash directly into the surface of Mars or be torn apart by gravitational stress before it gets there, its shattered remains potentially forming a temporary ring around the planet before eventually raining down onto the Martian surface, a slow-motion ending playing out over a time scale so vast it is difficult to hold in your mind for more than a moment. Deimos, by contrast, orbits much farther out and much more slowly, appearing from the Martian surface as little more than a bright star-like point of light, rather than a visible disk, offering none of the dramatic presence of Phobos, but instead a quieter, steadier companion drifting far off in the Martian sky. Together, these 2 small doomed moons offer a strange kind of perspective. Compared to Earth's moon, with its stabilizing gravitational influence and its slow, patient retreat that will continue for billions of years yet, Mars's companions feel almost temporary, fragile, borrowed rather than permanent, a reminder that not every planet gets a moon built to last. And in a small way, it deepens the mystery of just how fortunate Earth's own arrangement may actually be. A single, large, stabilizing moon formed in violence billions of years ago, holding our axis steady and our tides rhythmic, while one planet over, two small potato-shaped rocks quietly count down the millions of years until their own gravity finally pulls them apart. Quiet ending. Step back now, far enough that all four of these worlds fit into a single frame, the way the Voyager spacecraft once looked back from the edge of the solar system and caught our own planet as nothing more than a pale, barely visible speck suspended in a sunbeam. From that distance, Mercury, Venus, Earth, and Mars are simply four small points of rock formed from the same swirling disk of dust and gas warmed by the same star, and yet carrying such wildly different fates. One became an iron heart wrapped in almost nothing, its sky playing tricks with the sun itself. One wrapped itself so tightly in greenhouse gas that it became hotter than the planet closer to the sun, hiding volcanic plains and crushing pressure beneath clouds bright enough to be mistaken for centuries for a gentler world. One, through some fragile combination of size, distance, a churning metal core, and a single, oversized moon, became something rare enough that as far as we currently know, it stands alone among trillions of worlds, a place where water could pool in oceans and life could take root and eventually look back up at the sky and start asking questions. And one dried slowly into rust, its atmosphere bled away into space over billions of years, its ancient riverbeds now empty, waiting patiently under a thin, cold sky for the day, sometime in the coming decades, when human beings might finally walk across that dust themselves. None of these outcomes were guaranteed, and none of them were entirely accidental either. Each planet's fate emerged from the same basic physics, playing out slightly differently, depending on distance from the sun, on size, on the timing and violence of ancient impacts, on whether a planet happened to keep a churning liquid core or a moon large enough to hold its tilt steady across deep time. There is no single lesson to draw from this, no tidy moral, only the quiet recognition that four planets born from the same material can drift so far apart in destiny, and that our own world, ordinary as it feels standing on it, sits somewhere near the narrow, fortunate middle of all the ways a rocky planet can turn out. Perhaps that is enough to carry with you as you look up tonight. Somewhere above you, low near the horizon, in the hour after sunset, or bright before dawn, one or more of these worlds may be visible right now, small points of light indistinguishable from the stars around them, each one hiding an entire planet's worth of storms, silence, and slow geological time behind its faint and steady glow. We still do not know why Venus spins backward, or precisely why Mars lost its magnetic field, or what secrets remain buried beneath Mercury's cratered ice. Some of these questions may be answered within our lifetimes. Others may simply remain open, quiet, unresolved, the way the best questions in astronomy usually do.